Hello everyone, I'm Thomas Capelle, machine learning engineer at Weights and Biases, and today we will present you diffusion on the clouds, how to leverage diffusion models to perform short-term solar energy forecasting. Go for it, Alexis.
Hi, I'm Alexis Saint-Jean-Chomet. I'm an R&D engineer here at Steadysun, and I'm going to be presenting what motivated this study with Thomas. So we focused this study on solar forecasting for photovoltaic production. As everyone may already know, solar energy has enormous potential, but it also has a major drawback, and that's its instability. A cloud passes over a power plant and the power production can drop by up to 80% in a matter of minutes. So this behavior heavily impacts the whole value chain and the global stability of the power grid. It affects, in turn, all the actors down the line, such as grid operators, power plant managers, microgrid systems, such as insular systems, and energy trading actors as well. Here at Steadysun, we provide these actors with accurate solar forecasts at various timescales to help mitigate the risks and reduce the costs associated with production uncertainty. To do that, we rely on different products, but for this study we focused especially on the satellite imagery one. It enables short-term forecasts from a few minutes to several hours ahead. In this solution, we rely on geostationary meteorological satellites that provide multispectral images and that allow a global coverage with a spatial resolution of 1 kilometer up to 500 meters and a temporal resolution of about 10 to 15 minutes. Using these images to forecast solar irradiance is quite a challenging task because of the size of the data, because of the variety of the bands that are used. The algorithm is computationally intensive. On the other hand, the algorithm has also to output its results quite fast for the forecast to remain relevant. Luckily for us, we have access to Nvidia hardware through the incubator program. Our existing workflow uses first a step of cloud detection to identify clouds in the image and to estimate their optical properties, mainly their transparency. Then the last 6 cloud masks are combined to infer the cloud movements. Clouds are then propagated using optical flow to simulate the evolution of their movement in the future. Optical flow is a powerful tool that performs great in case of advection, when clouds are keeping more or less the same shape and are simply moving across the sky. But it reaches its limits in case of convection or local cloud formation or dissipation. It also cannot predict what's outside of the image, resulting in problems at the boundaries that spread out the more the forecast time passes. Moreover, any imperfection in the forecasts results in a big uncertainty. Because of the scale of the image, if a cloud is placed, let's say 1 pixel off from its ground truth position, it is equivalent to a kilometer or more offset in reality, and consequently a power plant can falsely be under a cloud or vice versa.
Thank you, Alexis, for the clear motivation. So how do we leverage diffusion models to solve these problems? What we're going to do now is formulating the problem as a next frame prediction task. Given a context of frames, we're going to create a model that is capable of predicting what happened next. Let's consider 3 consecutive images from the satellite. Let's play a game. Can you guess what's going to happen next? The cloud disappeared. I was not expecting that. Guessing that that's going to happen, it's not easy, even for the trained eye. Our task will be to put together a model that is capable of representing all these complex atmosphere behaviors. I would say that we have succeeded if we are capable of building a model that can deal with that. Luckily for us, we have a new tool on the toolbox. Denoising Diffusion Probabilistic Models, DDPM. These type of models are extremely capable of generating high-quality images that look sharp and detailed. Previously, if one wanted to generate high-quality images, you will need to use something called generative adversarial networks. These neural networks were complex and hard to train. So I would agree that the simple nature of diffusion models make them very useful for solving different new tasks. So how do you train a diffusion model? Let's deep dive and see what happens. Diffusion models consist on training a neural network to iteratively learn how to remove noise from an image. You start with a dataset of images and you noisify them using a scheduler. Then you teach the model how to remove different amounts of noise at the image. At the end, you will have a model capable of generating images from pure noise. If you want to learn more about diffusion models, I encourage you to read the Illustrated Stable Diffusion article. The neural network that we are going to use to train the diffusion model is the unit. This architecture has been on the deep learning field since 2015 and has been used to solve many image-to-image tasks. We will train the unit to predict the amount of noise of the image. We use a slightly modified unit that adds self-attention layers on the deep-down convolutions. But the diffusion process expects one input image, one output noise. So how do we frame this next frame prediction as a diffusion problem? I like to iterate fast, so first we're going to work on a simpler problem. We're going to work with the Moving MNIST dataset, but we're going to construct our own version of it. So what does it mean, Moving MNIST? As the name says, it's just the moving digits of the MNIST dataset. Basically, we're going to apply a affine transform iteratively, translate, scale, rotate, and shear to the digits of the MNIST dataset. That way, we will construct trajectories of moving digits on a canvas. Luckily for us, Torch Vision has affine transforms, so we can leverage that and create a dynamic dataset that has as many data points as we want. You can see that on Papers with Code, this dataset already exists for video prediction, but we are going to create a slightly more complex version that takes into account rotation, translation, and scaling that normally are not taken into account when considering Moving MNIST. This is because we are going to need that for the clouds afterwards. I'm also pretty impressed that none of the top models on Papers with Code use diffusion. How do you transform multiple frames into a single image? One trick is to stack them together on the channel axis. This way, we are able to feed the unit a single image that contains the information of the past frames. To do so, we only need to modify the first convolution layer of the unit with the corresponding image dimension. Now that we have a model that's capable of ingesting a new type of data, we need to modify the noising process, so our neural network is capable of denoising only the last frame. This simple conditioning technique enables us to train directly with the same unit that was used for the original DDPM paper. So now the training process looks like this. We feed the unit this fat tensor that contains the past frames and the noisy last frame. The output of the model is the predicted noise on the last frame. And we train this model with mean square error, comparing the actual noise with the predicted noise. Units are expensive to train as they require high amounts of memory. So this denoising process is trained using an A100. Luckily for us, these GPUs are equipped with a lot of memory. Having access to these high-end GPUs enables you to iterate fast and try different configurations, making the process of developing these experimental models much easier. The code was developed on PyTorch, and I encourage you to use the Nvidia containers for PyTorch as they provide the fastest possible implementation of PyTorch on Nvidia hardware. Another thing to note is when training this type of generative models, it's not enough at looking at the loss value. As you can see from this screenshot, the training loss flattens out pretty fast. But if you scroll and look at the model predictions over time, you will realize that It takes some time for the model to develop high quality outputs. So sampling the model regularly is very important to assess the model performance over time. Here, we are monitoring the training process with weights and biases, and we are logging image regularly to the dashboard, so we are able to explore and go back in time and see how the model training went. Let's not forget that we are going to use this model afterwards to create new frames. So the denoising capabilities are great, but what we actually want is sampling from the model from pure noise and generating a frame from scratch. Another cool perk of setting up the training process like this is that we can sample the model in an autoregressive way. What this means is that we can take the model's output as input for our next generation. This way, we are able of sampling the model as long as we want into the future. As my training code was using weights and biases, I can go back to the workspace and show you exactly what happened during training. Let me show you the training run. As you can see here, you have the relevant metrics during training, like the learning rate value, the epochs, and the training loss going down. Also, we have access to the logged images sampled from the model during training. As we move the slider to the right, we see that the sample image gets better. Let's head to the overview tab of this run. Here, we can see the Git repository that was used for host the code. Also that we use an A100 with 40 gigs of VRAM. If we scroll down, we see some of the hyperparameters. For instance, that batch size was 256. We can also click on the system metrics and get information about how the GPU was used. These peaks on the GPU utilization come from the sampling process. Also, we see that the memory allocation was pretty heavy, almost at hitting 100% all the time. Once you are happy with the results you see on the workspace, you can share them with your team or with anyone on the internet through a report. Here, I wrote an article explaining how we put together a dynamic moving MNIST dataset and we train a diffusion model for the next frame prediction. This way, I am organized and I don't lose any more results from my deep learning journey. Okay, let's go back to our original problem. We have trained them all on the Moving MNIST dataset, but now we need to train it on the more complex cloud dataset and see if our diffusion pipeline works to generate clouds. Let me show you the data from the satellite first. Here, each square represents 1 day of data for each band. The leftmost bands are the visible bands, and you can see that they start at night and they end at night. So you have a lot of information that get lost here. If you move to the right, you have the infrared bands. So they have an infrared camera that takes the temperature of the surface. So with these bands, we get more information during the day and night. We're going to use some sort of combination of these bands to train our neural network to predict the next frame of cloud movement. If we go to the workspace, for a research project like this one, it's not rare to have more than 100 runs like these. Let's switch to table view and take a look at the different experiments that were performed during this project. We can see that we have tagged the projects correctly, so we can identify the runs. Here we have a small model that trained in under 40 minutes, a UVid model that trained in 1 hour, and the bigger model took more than 13 hours to train. We can also see the relevant parameters like image size and epochs at a glance. Let's open VitalJazz, the training run that trained the small model, and explore the results. Here we get the same sampling over training images that we saw before for Moving MNIST. We can scroll on the slider and see how the model generations gets better over time. We can also inspect the resources used for training, and we can see that the GPU was used with good memory allocation. To keep everything organized, I have exported some of the results into a report. For instance, we added a batch of data with the previous frames and the noisy last frame for reference. If we scroll down, we have the results from our first model training. Here, we have a summary where we can see that the model was trained on images by 64 by 64 for 100 epochs, using 50% of the full dataset. On the left, we have a table with generations comparing to ground truth. This model is generating from 3 frames, generating 10 future frames. Let's click and open one of those generations. Here, we can see that the model is successfully making the cloud disappear in the future frames. This is something that we were not able to do with Optical Flow. If we scroll down, we have the same training metrics that we show on the workspace. We also have the same sample over time slider. Another nice aspect of these type of models is their non-deterministic nature. What does it mean is that we are generating future from noise. So we can use different noise to generate different futures. This could be seen as a drawback, but depending on how strong the past frame conditioning is, we will get different future predictions. Let me show you with more detail what does this mean. If we take a look at a sequence of images, if we condition on 3 frames and generate 10 frames on the future, we get slightly different predictions. As we move further into the future, for instance at t+8, we can see that the model produces different outputs. So as you can see here, the cloud is slightly different with different shapes and different forms. Let me show you the results of the bigger models training. So this is the same DDPM model, but trained on twice the image size. It's still not using any fancy trick like exponential moving average or fancy scheduling. So you can see here, if we open the table, we are generating 3 possible futures for every single input sequence. Let's scroll and open one. Here we have a cloud moving to the top. I like opening them like this, where you have the sequences on top of each other. So you can see the last frames look similar. As we want to produce high-resolution images from these models, we have multiple options. What I'm showing you now on the screen are the encoded images through the Stable Diffusion VAE. This is one trick you can use that downsamples the images up to 64 times in size, so then you can use your diffusion pipeline with these small-sized latent images. This is called latent diffusion, and it's what Stable Diffusion used to sample high-quality images. I'm pretty impressed that the Stable Diffusion pre-trained VAE works very well on these types of satellite imagery. I'm pretty sure there is none on the dataset that was used for training. Let's scroll to the bottom and let me show you the last model I trained. This is called Simple Diffusion and replaces the unit with a full transformer architecture. This model takes as input full-size images, so no more 64 by 64 images. The results are extremely good, and it's also very fast to train because the A100 GPU it's very efficient on multi-head attention. Here we can take a look at some generations. This is a tough one. I'm extremely pleased with the results of this later model. They look smooth, and it's great working on full resolution images. Going back to the slides, Alexis will explain why it's so important to get a non-deterministic forecast.
Having a set of non-deterministic forecasts is actually quite useful in the context of solar energy forecasting. Indeed, it enables calculating confidence intervals for each forecast by computing statistics on the ensemble. These intervals account for the chaotic nature of the atmosphere and the associated forecast uncertainty. In a sense, they represent the best and worst cases scenario. Generally speaking, grid managers and power plant operators prefer these kinds of probabilistic forecasts because they enable anticipating corrective actions to be made. In the end, cloud forecasts are only a part of the problem, and as we already explained, a small cloud position error has a great impact on the precision of our final result. Even more so when we integrate our work in the whole chain, where other steps already produce some uncertainty. That's why we are also looking at other AI or deep learning end-to-end models. They will take in some satellite imagery along with maybe other data and provide us directly the irradiance results.
Hello again, let's wrap it up. We are still on the early days of generative modeling, and we're seeing models out every day. I'm pretty excited with all the new technology that has been coming out. I am following closely what's happening with video and all these startups that are working with generative AI for video production. There is a ton of overlap on what we are doing here and what it's being applied to video. All this would have been possible with the access to Nvidia 8100 GPUs. I'm really grateful that we have access to these types of GPU that lets you iterate really fast on this huge data set. This is still a proof of concept. We are far away from deploying one of those models, but the results look promising. In this work, it has been shown that even simple diffusion model pipelines are capable of leveraging the high quality, high resolution to apply to future frame prediction. For me, the most impressive results come from dissipation and formation of clouds, something that's not possible to do with optical flow or traditional advection models. Also to note, there are no border issues as we are not moving pixels from the border. I have done some testing about VAE autoencoding, and you can actually encode these high-resolution images with a VAE like the one from Stable Diffusion. But recent work like the Simple Diffusion paper proves that you can work directly on the high-resolution space without need to pass through latent space. The cloud diffusion part is just one block of the pipeline. We have yet to couple this with the projection on the ground and then the computations of irradiances. Another area that could be explored is training an end-to-end pipeline that produces directly the time series forecast from the input images. Another aspect that could be explored is augmenting the data with other sources, like NWP model outputs and in situ observations. Thank you again for your time. If you want to learn more and find the codes to train your own diffusion model, go to 1db.me/GTC 2023.